All right, so I'm going to go ahead and start back where we were talking about, which is talking about quadratics. Quadratics is also known as parabolas, right? They are equivalent terms, so I can substitute one in for the other, and I'm talking about the same thing. It forms the U on a coordinate plane, which looks like this or like this. So we have a minimum here. We have a maximum on this one. When the parabola is going up, that means that it's going forever right and left. So our domain is all real numbers, and it's going forever up at the point of the minimum. So that means the range would have to be y is greater than or equal to whatever the y value of the vertex is. If it's going down, that means it's going forever right or left. So the domain again is all real numbers, but that means also there that the range is going forever down past the point of the maximum. So in this case, when it's facing down, the range is limited in y is less than or equal to the y value of the vertex. Got it? Okay. Circle back. Now, still talking about parabolas. We got this. Here is my vertex. This also means that my vertex is a part of my, my vertex is a part of my axis of symmetry there. So the x value of my vertex is the same as my axis of symmetry. Got it? Okay. So this has a minimum. This one is a minimum. So I'd say, oh, the domain is all real numbers, and my minimum would be what? Somebody tell me here. So take a look at this. What would the minimum be? Is it greater than or less than? And what is it greater than or less than? Okay? So, again, I'm going to say that my domain here would be all real numbers, all reals. And my range, because there is a floor, a minimum, that means the range is going forever up at the value of my vertex. So in this case, I'd say my range, my y, has to be greater than, going up, right, or equal to the lowest y value. What's the lowest y value going to be? The vertex. So this vertex is 0, -2. So that means my range is going to be greater than or equal to -2, because it can go from -2 up forever. So my range then would be y is greater than or equal to -2. My domain is all real because it's going forever right and left and up. Okay? For my next one here, again, anytime it goes up or down, that means it's forever expanding. So again, my domains are all real. My range is what actually has a limit. And in this case, it has a maximum. So that means if it has a maximum, the range is going forever down. The range is going forever down at this point. So since it's going forever down, down means less than or equal to. Well, it's going down past the point of its maximum. So what is a maximum y value? The maximum y value would correlate to the y portion of the vertex. So my vertex here, 2, 3, 4, 5, 6. Let's just say it's at -3, +6. So I would say, oh, it has to be less than or equal to +6, because at +6, it's going forever down. It's going forever down and forever right or left, because notice what's happening in this parabola is it's expanding. It's going outward. Okay? Got it? All right, good. So minimum, maximum, all real domain. Y is greater than -2. So when there's a minimum, y has to be greater than because it's going up. When there is a maximum, y has to be less than because it's going downward. Okay? All right, now I want to talk about how I can sort of work smarter, not harder, when I'm looking visually at a graph. So when they give me the graph, how I can determine, okay, what should my A and the ax squared be approximately? Work smarter, not harder. Here's what I know. When a graph is really wide, think of it in terms of a slope. When it's really wide, that means I'm like going up and out a lot. So I'm going up, but out a lot. Well, in a slope, it's rise over run. So for me to go out a lot means that I must have a denominator that's probably greater than my numerator. To be really wide means that I must have a denominator that's greater than my numerator. So it means I'm dealing with a fraction. So the bigger the fraction, or rather the bigger the difference of the fraction, the wider it's going to be. So let's, right? Following me there? The more narrow a parabola is, that means the more it's like a whole number. Because that means that my denominator must be smaller than my numerator. Because to be narrow, that means I'm going to be going up or down and right or left just a little. I'm only going right or left just a little every time. So that means, in simple terms, the wider it is, the bigger the denominator. The smaller it is, the smaller the denominator. So, whoop. All right. To recap, here's my y equals bx plus c, which I can also rewrite as y equals ax squared plus c. Or I'm sorry, y equals if it's in this format, right? Okay, so what we know, again, our axis of symmetry, anytime it's in this format, anytime it's in the format of y equals ax squared plus c, or just y equals ax squared, right, the parent function, then I know my axis of symmetry is the y-axis. What does that mean? That means your parabola must be going up or down, because the y-axis is vertical. So for the axis of symmetry to be vertical, that means it's being reflected left and right. Right? Okay? So anytime it's in the form of y equals ax squared or ax squared plus c, then you know your parabola is going up or down because it's reflecting over the y-axis. So the axis of symmetry will always be in the form of x equals, because if I'm reflecting over the y, then that means my axis of symmetry is passing through the x-axis at some point. Okay? All right. The other thing I want to talk about is how can we look at a parabola and work smarter, not harder, and determine, sort of derive information from just looking. What I know is that in the ax squared plus c, the a, this is really similar to y equals mx plus b. So the a is kind of like the m, the slope. The a tells me a lot. Positive a tells me it's up, negative a tells me it's down. Well, also, if the a is a fraction where the denominator is bigger, like I was talking about, than the numerator, then I know it's more wide, because that means I'm only going up a little but out a lot. So when my denominator is bigger, I know that it's really going to look wider. When my denominator is smaller, meaning I'm going up more and only out a little, well, then it's going to be more narrow. Okay? So I'm going to keep that in mind. I'm going to look at these three graphs right here. Very wide, kind of wide, this one's more a little average, and then narrow. And I want to align it to these three equations. I want to know which one matches with which graph. So when I look here, my a is negative. Right away, I should know exactly what that one is because it's negative, so it's the only one facing down. Process of elimination, boom, this is the one I'm looking at. Right there. There we go. Notice also that, well, it is narrow. Why is it narrow? Because what it's telling me is that I'm going down 4 to the right 1, right? Because every whole number is over 1. So when my numerator is bigger than my denominator, the more narrow it is. Because that means I'm going down 4 and to the right only 1. So that means the distance between them, right, on the x-axis is more narrow. When I look here at this 1/4, notice that this is positive, so it's going to be going up. So I'm in between this one or this one. Well, what is this telling me? This tells me that I'm going up 1, but to the right 4. Well, if I'm going up 1 and to the right 4 on each side, that means that's a pretty big difference of 8. So up 1, out 4 on each side means that this should be pretty wide. Going back to when the denominator is bigger, The bigger the difference between the denominator and the numerator, the wider it is. So this would match up to, ding, 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 this one right here. And finally, my last one, what is my slope here? This would be a 1 over 1. That means as I'm going up 1, I'm going out 1, up 1, out 1, and then on each side. So this one is more consistent. It's just your basic peripheral U. So one last time. When my numerator and denominator are consistent, it's going to look like your basic U. When my numerator is greater than my denominator, the more narrow it gets. When my numerator is smaller than my denominator, or my denominator is bigger, the wider it gets. Okay, so we want to keep that in mind. It goes right back to sort of a basic. You may want to write a thought bubble, something similar to this. But remember, numerator bigger than, when numerator is bigger than the denominator, it's more narrow. When the denominator is bigger than the numerator, it's more wide. Okay? Next thing I want to look at is a comparison between this graph and this graph. Notice they both are in the form of y equals ax squared plus c. So that means it's starting at the origin. So my vertex is at the 0, 0. So how can I tell the difference? Well, I could make a function table, so I could pick numbers for each of them. In this case, I'm going to pick 0, 1, and 2 for both. And what we'll see when we plug it in is, well, when I plug in the value of 0 for the x, so 2 times 0 squared versus 2 times 0 squared plus 3, right? So 2 times 0 squared is 0. 2 times 0 squared, 0 plus 3 is 3. So right away we can see, comparing the 2 points, okay, we got a little bit of a difference here. But all of you should remember that this plus 3 means simply that the graph, instead of being at 0, 0, is starting at 0, 3. So this is what we're looking at here. Here is my y equals 2x squared, right? Because I started at the 0, 0, and I'm going up 2 to the right 1, up 2 to the right 1, or I could plug it into the function table and get a series of coordinates. Y equals 2x squared plus 3, then what that means is instead of starting at 0, 0, my vertex starts at 0, 3. So really it's just simply shifted up 3. So I'm going to be going like this. So the shape, the shape is the exact same, the width of it, everything, because the slope, the A, is the same. So it's not wider or narrower. The only difference is that it went up 3, which takes us right back to the whole x minus h squared plus k. This was a change on the plus k. The plus k portion is how it goes up or down. So in this instance, the change was happening to the y value, which means I simply took my original graph and I just went up 3. That's your change. Please, I want to look at right here a question such as an acorn drops from a tree branch 20 feet above the ground. Here is my function. Height gives it gives the height after t seconds. So looking at this, basically the height represents my y, the time represents my x. Well, what can I derive from this? One, this parabola is going down. It's starting at the 20 because 20 is just like your b, right? My y-intercept there. Negative 16 means it's going at a rate of down 16 to the right 1. So for every half second, it's going down 16 feet. That's what basically I can determine from that. So if it's starting at 20 feet, then at half a second, it's at 4 feet. And so now I was able to graph this. So the question really is, all right, well, when does it hit the ground? So it's going to hit the ground when the height is at 0, which means I need to know my x-intercept. How you go about doing this is you simply set up a function table. I know when x is 0, my y is 20 feet. Well, when x is half a second, my height is 16 feet. How did I get that? Right here, plugged in the function. And I could keep on plugging in until I find approximately where it's going to cross. And that's what I did. It's crossing between 1 second and 1.5 seconds, because at 1.5